Hi friends, today on 1 Minute Math, we're looking at trigonometry on the unit circle. This is probably a pre-calculus concept, maybe Algebra 2, or maybe you're in AP Calc and you need some review, or you're in AP Physics trying to get some review on how to evaluate trig functions on the unit circle. So the kind of context I'm thinking here is you've been presented with this expression, sine of 5 pi over 6, or something like that, and you're supposed to come up with a number that equals. And you're like, oh my gosh, I don't know how to do that. So a couple quick reminders before we jump into how to use the unit circle. Hopefully you've done trigonometry in geometry class. You might remember SOHCAHTOA as an acronym. In SOHCAHTOA geometry, that would be something like, if I'm looking at this picture right here, I've got a triangle. If I was looking for this x value, I recognize that I've got an opposite side, an adjacent side, and a hypotenuse. That's how I label the sides of my triangle in SOHCAHTOA trigonometry and right triangle trigonometry. The 12 and the x are of interest to me in this situation. I'm looking for x, and 12 is a number, and I need some kind of leg to stand on. So that's why I come up with sine. OH, opposite and hypotenuse are the interesting numbers or interesting sides to me. OH means I need to use sine. I set up a fraction that looks like this, sine of 50 degrees. Sine, cosine, and tangent are functions. They are operators where I put an angle in and I get a fraction or a decimal out. So 50 degrees is what I put into my calculator. I just type that into my calculator and it spits out this random decimal, okay, 0.766. That means 0.766 equals x over 12. I can do some algebra and find my x value, and that in this case would be 9.193. That would be the value of x. Okay. So that was a quick overview of how to use right triangle trigonometry, or SOHCAHTOA. If you need a cheat sheet, here you go. SOHCAHTOA means sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent's opposite over adjacent. I'll scroll up to the picture again for a moment. There we go. And we also will want to know these concepts from geometry. Special right triangles is what I would call this. If I have a right triangle with angles of 45, 45, and 90, which makes it isosceles, then I know that these two sides are the same. And you can do the Pythagorean theorem and figure out the third side here, the hypotenuse, would end up being 10 times the square root of 2, or 10 roots of 2. So this pattern always holds. If I had sides of 3, it would be 3, 3, and 3 roots of 2 if I have an isosceles right triangle, if I've got an angle of 45 degrees. Right, this is going to be important to us in a minute. And also this guy, 30, 60, 90 triangles, which are just, if I have angles of 30, 60, and 90, I can make a mirror image of that angle and come up with an equilateral triangle. That's the trick for solving these if you forget the cute little rule. But it ends up, so because it's like half an equilateral, let's say I know that side is 10 and this is a 60-degree angle. I could say, oh, well, if that side's 10, this whole side is 20. That makes the hypotenuse here 20. Do some algebra and get that will be 10 roots of 3. And here's our pattern here. Well, whatever this short side is, the hypotenuse is twice it, and the longer leg is the square root of 3 times that short side. All right, geometry review over. Now we're going to jump into this thing called the unit circle. So I'm just going to present a short problem, and that will kind of springboard us into how we define sine and cosine when we're talking about this circle. So just for funsies, we're going to say the angle that's right here is 60 degrees, and the radius of this circle is 1. So in particular, like this length would be 1. Also, we'll note that this length here, the distance from the center of the circle out to P, that's also 1 because it's a radius. And we're asked to find the coordinates of point P. So the key here is that if I'm looking for the y coordinate and the x coordinate of that point, that actually makes a cute little right triangle right here. All right. And that x and y coordinates being the legs, the short leg and the long leg of a right triangle, means I can use SOHCAHTOA trigonometry to get those values. But even more important than that, like let's say it was 80 degrees or something where I didn't know how to use a special right triangle to get there, I could set up my situation. I'm going to call this theta. Are we okay with that? This is the Greek letter theta. Theta. It makes the th sound in Greek. So if I was going to write the word math, I would write mu alpha theta, math. Okay, that's the theta. We usually use him to represent angles, and this is one. If I were to write out my SOHCAHTOA statement, it would say sine theta is y over 1. And you're like, oh my gosh, that means it's sine theta is y. Yes, you're exactly right. But anyway, we've got a special right triangle here. So just for funsies, we're going to use our special right triangle rules and go back a couple seconds in this video if you forget those. The short side, the short leg is 1/2 of the hypotenuse, and the longer leg is that smaller number times the square root of 3, or I'm going to write this as √3/2. That's typically how we write this. √3/2 and 1/2. So the coordinates of P will be 1/2, √3/2, right? Triangles, circles, living together on a coordinate grid. We get all the major shapes that define our world all together, living here in one situation. It's great. I love the unit circle. So here on the unit circle, if I had any point, let's just say this point was over here, and I did the same thing, and again, I didn't know a special angle. Let's say it was 10 degrees. I'm going to point out here that in my triangle, y, x, 1, the sine of 10 degrees would be y/1, which is y, and the cosine of 10 degrees adjacent over hypotenuse would be x/1, which is x. The moral of the story is that, next page, sine and cosine can be defined as the x and y coordinates of the point. If an angle theta is drawn in the coordinate plane, so that its vertex is at the origin, and one ray lies along the positive x-axis, so it'd be this guy right here, and one ray, and centers at the origin, vertex at the origin, and a circle of radius 1 is also drawn on that axis, then the point at which the terminal ray, that's this guy over here, meets the circle x comma y gives the sine and cosine of theta. The sine of theta is the y coordinate, the cosine of theta is the x coordinate. Here's the stupid way I remember that. Sine is y, siney, that rhymes with hiney, which is stupid and silly, and now you're never going to forget it. Siney like hiney. Sine goes with y, cosine goes with x. Cosine comma sine, always. So if I ask this question now, an angle's drawn in the plane, so one ray rises along the positive x-axis, and the other ray intersects a circle of radius 1 at the point -0.6, 0.8. 0.8, -0.6. There's my angle. This is where it intersects the unit circle. What are the sine and cosine of this angle? The sine is 0.8. And the cosine is -0.6. It's that easy. Cosine's x, sine is y, bam. So how do we use this? And here's a good picture too. Take a mental snapshot of that guy if you need it. Here would be another one. If I asked you what's the sine of this angle alpha, it's just the y coordinate. The cosine of that angle alpha is just the x coordinate. The nice thing about defining sine and cosine this way is that I can talk about angles that are, I could get the same point by going clockwise. I could have this large angle. It's like 300 degrees or something, right? It's like all the way around the circle almost. And I can still talk about the sine and cosine of that. I could ask you for the sine of 90 degrees, which if I'm stuck to the right triangle definition, the SOHCAHTOA definition of sine and cosine, this question makes no sense. I can't draw a right triangle that has another 90-degree angle. That's not a triangle. But if I define sine and cosine this way, talking about the unit circle, there's my circle, and this has a radius of 1, so I've got points here like 1, 0, 0, 1, -1, 0, 0, -1. Okay, now I can talk about the sine of 90 degrees. Just go 90 degrees. Sine is the y coordinate, and the answer is 1. The sine of 180, all the way over here, 180 degrees. The y coordinate is 0. Sine of 270, you get the idea now, right? If I go all the way 270 degrees, that's down here, the y coordinate is -1. So while these things don't make sense in triangle land, like to have a sine equal -1 on a triangle, that doesn't make a lot of sense. It makes perfect sense here in unit circle land, and this is why the unit circle is actually a better definition. It has more inputs. There's no angle, there's no number. If I ask you for the sine of something, there's no number that I can't put in there. Cosine, let's just do one of these here. Cosine of 90 would be the x coordinate is 0. Cosine of 180 is -1. The cosine of 270 is also 0. Good. So that's how we use the unit circle. We're going to skip that slide. We've reminded ourselves about those. So given our special right triangles, this would be a great exercise for you to do on your own. I'm not going to do all of them, but we have these 16 major points on the unit circle, like these guys, 1, 0. Okay, these are pretty easy. And then these things, like this would be the angle pi sixth. I have another video that relates radians to degrees. I would encourage you to go watch that. We'll talk about that here in a moment. I'll go ahead and go back to degrees for a second. But when I'm talking about like angles on the unit circle, we typically measure those angles in radian measure, which is just another unit for measuring angles. It's very, very similar to measuring angles in degrees, but yeah, we'll get to that in a moment. Anyway, let's call that 30 degrees. If you ask me for the x and y coordinates of this point, I can find those using special right triangles. I'm going to remind myself that, like, I'm going to call it triangle instead of x. That's my pattern for 30, 60, 90 right triangles. So if the hypotenuse is 1, that means the short leg is half of that. And this long leg is going to be this number, which would be 1/2 times the square root of 3, which we typically call √3/2. That makes the coordinates of this point √3/2, comma 1/2. Okay. And I can use symmetry to say, oh, the coordinates over here are going to be the same, except the x coordinate is negative. And the coordinates down here are going to be the same, except the y coordinate is negative. And over here in quadrant 3, both x and y are negative. So I would really encourage you to take the time to find these on your own. Pause this video or come back later and take the time to find all the coordinates of these points. I'm just going to show them to you in a moment. We're going to do one more here together because the 45 degrees can be a little bit tricky. If we remember our pattern for 45, 45, 90 triangles, it was x, x, x roots of 2. And if this is 1, that means that this side over here is going to be whatever times the square root of 2 equals 1, which would be 1 divided by the square root of 2. And there's this old rule that says we don't like square roots in the denominator, so I'm going to rationalize this denominator. And I'm going to call this thing √2/2. √2/2. So that's the coordinates of this point. And again, you can use symmetry to get the other green angles on this, the way I've drawn it here, and find those coordinates. Let me show you what it looks like here. Ooh, close. Sorry, one more. There we go. When it's all done, this is the picture you get. You can find images like this. Just do a Google search, you'll get an image. Print it out, put it on your mirror at home, stick it by your bedside, put it on your books, whatever you need to do. You need to memorize this thing. If you're in a math class where you are where you're being asked to evaluate trig expressions like AP Calculus, or maybe even in a physics class or something, you need to have this memorized. It's like the alphabet for higher level mathematics. And I trust me, it's going to make more sense. The more you look at it, the more you do it, the more sense it's going to make. We're going to take like a minute here to look at radian measure to talk about why these numbers are there. And I'm going to show you a trick for memorizing this. We'll do the other trig functions and then we're done. Okay, so radian measure. The radian measure of an angle. So let's say way back in ancient times somewhere, some dude drew an angle and he was like, oh, I want to measure how pointy these angles are. How do I know that one is pointier than the other? So dude one looked at this pointy part of the angle and was like, well, I'm going to measure it here. The pointiness here is about, I don't know, 40 degrees, whatever that means. The pointiness here is like 85 degrees. It's wider. It's less pointy. And then dude 2 says, oh, I'm going to go out here. I'm going to walk the same distance out on each arc and measure how far it is between them. And that's going to tell me how pointy or how wide this angle is. This measure out here is like, I don't know, 3.5. And this distance here is like 1.5. So I know that this angle over here is wider. This is the radian measure. The radian measure of an angle measures the distance along the edge of the unit circle from the one point, like the opening point of an angle, to the closing point of the angle. So if I wanted to find a few of those, like using the fact that 2 pi r measures the whole distance around the circle, and in unit circle land, I'm talking about a circle of radius 1, right? This radius is 1. That means that 2 times pi times 1, which would be 2 pi's, that's the whole way around the circle. Okay, so with that fact in mind, I could say, well, halfway around the circle, that distance would be 1/2 of 2 pi, or pi radians. right? And this distance up here from this point over to the 90-degree angle, that's a half of pi, or pi halves. And this would be a fourth of pi, and a sixth of pi, and a third of pi, and so on and so forth. A great conversion factor is that 180 degrees is pi radians. As with all things, when it comes to memorizing these things, an ounce of understanding is worth a pound of memory. So if you can remember that 2 pi's is the whole circle, because it's 2 pi r, and then you just look for fractions of that, you're going to be better off. That's how we get these. And again, I have a whole video that goes into more detail about how you generate these radian measures. It's important to measure angles in radians so that calculus works. Calculus actually falls apart if you try and measure angles in degrees. So if you're going into higher level math, you need to measure angles in radians. That's how we get this picture. So in that very first example I gave you, if I asked you for the sine of 5 pi over 6, you can totally do this now. 5 pi over 6, I found my angle. Sine is the y coordinate. That's 1/2. Easy peasy lemon squeezy, right? Let's talk real briefly about these other 3 trig functions. Oh, other 4. Tangent is sine over cosine, which makes it like opposite over adjacent, or opposite over hypotenuse over adjacent over hypotenuse. Sine is the y, cosine is the x. Tangent is y over x. Cotangent is the reciprocal of tangent. Secant is the reciprocal of cosine. You might wonder why secant isn't the reciprocal of sine, but there's a good reason for that. Keep going in calculus and you will understand, cosecant, why secant goes with cosine instead of with sine. And then cosecant is the reciprocal of sine, so 1 over x and 1 over y. So a classic problem here looks like this. There we go. Say I ask you for the tangent of 2 pi thirds. You got to find the angle. So presumably you've got this all in your noggin. 2 pi thirds, that is right here, because 1 whole pi is all the way over. So there's 2 pi thirds, I'm a good student who has memorized my values there. I found the x and y coordinates. I'll show you how to get them in a sec. That's the very last thing. The trig function is tangent. Tangent is y over x. So that tells me what to do with those coordinates. Y over x. Simplify if necessary. It is in this case. I can cancel the 2's. Root 3 over 1 is just root 3. So I get negative root 3. And that is my answer. That's how we use the unit circle. Now you're thinking to yourself, Mrs. Thomas, there's no way I'm going to memorize all that stuff. My quiz is tomorrow. Well, take one corner of your unit circle, draw your 3 angles. Okay? Here's a quick, easy way. Everything's over 2, right? It's always over 2. So over 2, over 2, over 2, over 2, over 2, over 2. Start at the top left corner and go 1, 2, 3, 1, 2, 3. Bam. And then if you get symmetry, right, get your x's and y's and your positives and negatives correct, this will provide for you all of the points on the unit circle that you could ever possibly want. All right, I hope that you found this helpful. Keep watching. Thanks.